Welcome everybody to the November Canada Wildfire webinar. This webinar is really exciting and going to build off of the one we had in October with Landon Shepherd looking at the Jasper Wildfire Complex. Our October webinar was from a operational lens. If you happen to miss that and would like to watch the recording, I'll make sure that we post the link to that in the chat box. Today, I'm really excited to have two presenters with us. We have Daniel Perrakis and Luke Collins, who are both integral parts of two reports that came out of the Jasper Wildfire Complex. So the first is Daniel Perrakis. He was the coordinator of the Jasper 2024 Wildfire Complex Documentation, Reconstruction, and Analysis report recently released from the Canadian Forest Service. And second, we'll have Luke Collins. He was a co-author and contributor to the Jasper Wildfire Community Impact and Research report released from FPInnovations. So today we're going to have both of the presenters providing a bit of a briefing on the reports that they were part of, and they're going to do them back to back. And at the end, we're going to have some time for question and answer period. So as typical in our sessions, please post any questions as they come up in the chat box, and I'll be sure to get to those at the end. And with that, I'm going to hand it off to Daniel. Daniel, welcome. We're really happy to have you here today.
Thanks very much. Can you hear me okay?
Yeah, you're great.
Great. So the first thing I just noticed, as some of you probably have picked up, is that on the title slide, it says this is the Wildfire Summit Conference. Is not. And so there's my embarrassing title slide, which has the wrong talk. Apologies to Canada Wildfire. Anyway, I'll jump right in otherwise. So yeah, thanks for the introduction. And, as many of you will have seen Landon Shepherd's talk or, heard about this event in the news or was heavily covered for a while. So the basic story is fairly well known, but I'll just quickly recap and then get into the work that we did as part of the documentation, reconstruction, and analysis team. So quickly, on the evening of July 22nd, 2024, lightning ignited a fire south of Jasper that quickly began spreading north towards the townsite. And together with the municipality, Parks Canada evacuated the entire park that night. And sorry, I'm just trying to find something here that is not, okay. Zoom is giving me some issues, but anyway, that'll be okay. So they evacuated that night the entire national park and everyone fled west into BC. The road east towards Hinton and Edmonton was actually blocked by a second fire, the North Fire, that started almost exactly the same time and was closer to town and initially drawing most resources and attention. And then 2 days later, on July 24th, the so-called South Fire reached the Jasper townsite and destroyed over 350 structures, mostly homes. So a few days later, Parks Canada reached out to the Canadian Forest Service to request help studying this fire. And so a team of fire behavior specialists was quickly mobilized, and several of us made plans and traveled to Jasper while the fire was still active. And our main objective, as outlined, our task to us from Parks Canada, was to offer a scientific analysis of the factors behind the rapid spread and extreme behavior of this South Fire. So briefly, to identify ignition and spread factors, document, fire behavior evidence from, objective scientific means, and examine fuel impacts, including any impacts from mountain pine beetle caused mortality, any effects of the hazard reduction treatments, analyze weather, including drought and wind effects, and identify other extreme fire phenomena, and reconstruct fire behavior, what happened near the town site as the fire breached the main Jasper municipal area. And out of scope of this analysis was, discussion of fire suppression tactics, specific impacts in the Jasper town site, although Luke Collins, working with FPInnovations, will be talking about those after my talk here, and also out of scope fire management policy and forest management practices. And of course, the main focus was on the Jasper South Fire, which was, quickly identified to be the one that caused the majority of the damage. So our team arrived on site in early August. The fire was still active, but much quieter than it had been in its first few days before it hit Jasper town site. So we conducted some extensive interviews and gathered records of photos and videos taken during this event. In fact, almost 10,000 files, video and photo files were retained and analyzed. And then we actually got out in the field for a few days and collected almost 250 rapid crown fire plots as well as 11 more detailed fuel consumption plots, and those were facilitated. We're very grateful to the University of Lethbridge Geography Department under Dr. Laura Chasmer and her students, who had some very valuable pre-burn data from the fire area they were able to share. And we also identified and collected some evidence on extreme fire behavior and did some fire-driven wind reconstruction and ember sampling. And then back in the office, we gathered a whole bunch of publicly available data from Parks Canada, from the Canadian Lightning Detection Network, from satellite imagery, and did some high resolution photogrammetry, and basically helped all these sources helped with our reconstruction and various analyses. So some of the basics, many of you will know this, but nonetheless, the fire area was a bit over 32,000 hectares in size, shown in the red outline. At the top of the figure here, you see the small separate blob, which is the north fire, but the majority of the area was the so-called south fire. And the purple, polygon there is the Jasper townsite, with the orange blobs around it are the mechanical fuel treatments conducted by Parks Canada over a 20-year period. The red circles with X's are the suspected ignition points of the south fire. And then the blue hexagons are the key fire weather stations that were used in our analysis. So there's a very good weather station network around this fire, and should have pointed to a fairly clear picture of what happened. But it was a little more complicated than that, as it turns out. So to begin with, the ignition. So this was very well established. The evening of July 22nd, around 1900, there were 3 separate lightning strikes causing separate ignitions. There's very high confidence in the location and timing, with the 3 separate fires identified by initial IA crews lining up very well with 3 lightning strikes from the Canadian Lightning Detection Network. There was a team of contractors in place, as the photo up on the top right shows, 6 minutes after one of the lightning strikes. And obviously there's a well-developed fire already visible, with tree crowns bending towards the plume and some obvious crown fire activity. So this is just 6 minutes after ignition. And then 90 minutes, there's an aerial team that went over, and obviously we have a well-developed crown fire at that point. So in terms of weather, the southernmost ignition point was very close to this Ranger Creek weather station, with the meteogram shown here in the bottom left image. And it may be a little hard to see here, but at the time of ignition, there was a convective storm, and there were sustained winds of about 21 kilometers an hour, with gusts to 87 kilometers an hour. So it was a very strong convective storm. And we estimate it was beyond ground crew suppression within less than 10 minutes, and probably beyond aerial suppression within about 20 to 30 minutes. And there's also citizens, motorists, who are traveling south at this time, and captured some video and got some social media attention. And this is actually linked. Their original videos are linked in the report. So they had beautiful, video like 2 to 3 minutes after the ignition, including one of the lightning strikes. So following these ignitions, the 3 fires merged within a couple hours, and formed by that evening, by 2300, a single perimeter over 3,000 hectares in size and 12 kilometers long, just a few hours after ignition. So the next day, which was the 23rd of July, the fire burned with sustained extreme behavior, including crowning activity, for about 13 hours, with crown fire behavior detected as early as 10 in the morning and as late as 2300, and also considerable overnight burning. And basically a lot of this was probably what we would describe as passive crown fire, or just sustained steady growth, but not explosive. So the fire advanced about 8 to 9 kilometers over this 13-hour period. And then overnight, spread was more upslope to the west. And in general, some of the fire environment factors that quickly were identified as critical, including high fuel connectivity with more or less continuous conifer fuels across the entire valley. The mountain pine beetle, which had killed the majority of lodgepole pines, which was the dominant tree species in the area. And that happened about 6 to 8 years previous. I'll get into some more details on that in a little bit. There were low observed surface winds. So other than that convective, gusty period of a couple hours at ignition, the winds overnight and during this day, the 23rd, were actually very low, less than 10 kilometers an hour at just about all the stations, with the exception of the high ridgetop alpine stations. There were severe drought conditions present in the area, and quite a few topographic interactions with atmosphere, a lot of evidence of complex factors beyond what simple weather station readings would show. The July 24th, the next day, as I noted, there was very significant overnight burning with a lot of hot spots, but not a lot of overnight progression. And in the morning of the 24th, there was a classic fire weather pattern of an overnight and morning inversion. And so the valley was socked in with smoke that morning until about noon. However, by noon, the inversion lifted and fire activity suddenly began explosively, and northward spread began at that time, led by a strong convection-driven plume, clearly visible in this photo on the left. So this is around 1400, showing convective behavior with column rotation. And this was a time associated with the most rapid spread of this fire. I think Landon may have shown a video of this. So there was about a half hour where it was measured at about 92 meters per minute and about 27 to 40 meters a minute for several hours sustained during that afternoon. 92 meters a minute is about 5.5 kilometers an hour. And so this type of plume-driven behavior is where, as we say, the power of the fire overwhelms the power of the wind. So this is not a wind-driven fire. And this was our challenge with these wind readings at the weather stations. They essentially, from all the evidence, suggest, were irrelevant. So the winds were light. The fire itself generated these tornado force winds, and this caused extreme fire-generated blowdown in addition to combustion effects. And the photo in the middle here is several days later when our team arrived on site. Large trees and pieces of the built environment were hurled around the landscape, sometimes in circular patterns, sometimes in linear patterns. In some cases, material was transported, 100 meters and even over a kilometer. Some of the trees that were green, in fact, were lifted or broken and hurled across highways. In some cases, stayed unburned. In some cases, they were within sprinkler lines of some of the built environment protected areas, such as commercial accommodations. So these were winds generated by the fire, and many of the wind-thrown trees were then burned. And it's not clear, what the timing of the burning was relative to the extreme winds. As the fire began to approach the town site, aerial ignition operations were conducted to lead the fire away from cabins and the town site and other structures. And unfortunately, we didn't have tools to evaluate whether these operations were successful or not. And as I noted, spread rates of about 1.5 to 2.5 kilometers per hour persisted for several hours that afternoon as the fire spread northward. So this is shortly taken about 12:30 that day. And here you can see the remnants of the inversion smoke layer in the valley, and then the strong plume that is developing very actively. And there's also in the distance some high clouds starting to arrive. And that ended up being quite an issue because it prevented most of the satellite detection potential that day. And as the fire approached the town site more closely, our reconstruction suggests that a number of interacting factors contributed to a column collapse and downburst event, which drove the initial pulse of embers into town and began the chain of destruction. So there is evidence that there were these fuel treatments, as I noted in one of the earlier slides, and these appeared effective, and I'll talk about that in a moment, at reducing fire intensity around the town site. But there were many untreated subalpine slopes, and intensity was clearly still extreme in some areas, 1 to 2 kilometers or more away from the town site. And it appears that converging winds from the south, Athabasca Valley, as well as from the west, the Mayette Valley, as well as the sudden loss of fuel as the fire reached alpine areas and tree line, probably together caused the convection column collapse. That was about 1740. And this is actually captured in the leftmost photo here when the helicopter ignition team, had landed on the highway due to overly hazardous flying conditions, and they captured some of this, where the column collapse produced strong, short-lived southwest winds over the town site around 1745 and thick, continuous ground level smoke. So that's the photo in the middle here. The visibility dropped, to less than 100 meters. Street lights were triggered by the darkness. And we suspect this was accompanied by the first pulse of embers into Jasper and the first structure ignitions. However, the timing and location of the source of embers and the timing of location of individual ignitions are highly uncertain at this time. The winds subsided by 1805, but the dense smoke lingered for another 30 minutes or so. And the radio log suggests that at that time there was a very significant urban fire event going on, and many crews were attending to those. Afterwards and during this time, the fire continued to spread in a north and northeasterly direction, south and east of the town, and eventually reached Roche Mayette and Grisette Mountain by about 2000, and significant rains actually began at that time and aided significantly in firefighting efforts and reduced fire behavior thereafter considerably. So our overall documented analysis suggests a range of technical findings that will be of great interest to fire behavior science and for practitioners. So the fire severity, so the magnitude of change, caused by fire was high to extreme over all this area. However, this is not surprising at all, given the fire behavior, and is quite comparable to many large fires in Western Canada these days. The fuel consumption, as I noted, thanks to these excellent 11 plots with great pre-burn data from the University of Lethbridge, fuel consumption was about 2 to 3 times higher than we would expect from healthy green conifer forests, and this appears to be due to consumption of the dead wood from the extensive mountain pine beetle mortality. So in some cases, there was several hundred stems of standing, significant, mature pine trees that were completely consumed with no evidence of them on the ground or standing. So completely consumed by the passage of fire. So very high fuel consumption. As I noted, the fuel treatments did appear effective at reducing crown fire and overall fire severity. So this graph on the top right here shows on the vertical axis is a modified crown fraction burned field measure. And then the 3 bars are no treatment on the left. On the right is the orange is the recent treatments. And then the sort of teal color in the middle is older treatments. And so there's clearly a significant difference here between the untreated stands with the much higher crown fraction burned compared with the recent treatments. And then the older treatments are somewhere in the middle. These differences are statistically significant from a Mann-Whitney U test, but you can see the clear variability as well in the box plots. So lots of severe fire evidence in all treatment types. These treatments are also sort of highlighted in these photos. So on the bottom, the 2 photos on the right here, the one on the left is an untreated stand showing the obvious loss of all the branch structure. So very, very significant consumption and deep charring of boles. And then the one on the right is a Douglas fir stand showing, whether or not those trees survive, there's still clearly an unburned crown structure on many of the large trees. And that would be a recent fuel treatment. The spread rate was much higher than expected from models. And as I noted, that's certainly because this was a plume-driven fire and essentially was not following the ambient external winds. And finally, fire intensity, for those who know the, probably the most famous equation in fire behavior, Byram's fire intensity, HWR, the weight, the mass of consumed fuel and the rate of spread together. This created some of the highest values recorded in Canada. And so these findings highlight, some of the need for some of the limitations of our models, some need for new research tools for these types of complex environments. So very quickly here, going through some of these elements individually, there was a lot of talk about whether, the mountain pine beetle effect was significant. So there's a lot of questions about fuel typing. Sometimes it's subjective, but a national fuel type layer that does not include any mortality effects, such as from the mountain pine beetle, suggested the vast majority of this area would have been dominated by the C3 mature lodgepole pine fuel type, with a few other fuel types present. So, this sort of light green color is the C3, and that would have represented the majority of this fire area in the absence of the mortality. The mountain pine beetle did come much later to the Rockies than to most of BC, for instance. So in the area of this fire, this was clipped from some vegetation, forest insect and disease surveys. And so basically it really began in earnest in about 2016, peaked in 2017 and 2018, and then essentially the outbreak collapsed. So this is the time of fire stands in the post-epidemic stage, about 6 to 9 years since beetle attack. And then again, very quickly, I noted this is about 32,000 hectare fire, about 27,000 hectares was in, mature conifer forest affected by the beetle. And some of the highest values, the single highest value was in the severe beetle attack category. Second highest was in the moderate. And then there's also about 4,000 hectares in the low. So together, about 74% of the area of the conifer forest area was in low, moderate, or severe beetle category. But there's also about 7,000 in very low, which were mostly subalpine Engelmann spruce, subalpine fir stands. Weather, of course, was a huge factor here. So although the spring and early part of the summer in Jasper were fairly moderate with abundant precipitation, this just shows noon temperature and precipitation. The background gray is a 60-year climatology from 1962 to 2023, showing the confidence intervals of temperature, noon temperature, and clearly in July 2024 here, a heat wave and dry period began with almost no precipitation and some record-breaking temperatures. And similarly, many of you will know the buildup index, or BUI, and again, the same climatology in the background here. The black line is 2024. And so again, the beginning of July, the BUI was very average at the beginning of the month, and it just started to climb very, very steadily, eventually reaching near record conditions at the time of the fire, which is shown in the dotted line, the dotted vertical line. And we did compute an estimated enhanced or effective BUI, which basically simulates the extra drying effect due to the loss of the foliage from the mountain pine beetle mortality. And that's in that light gray line. And if that assumption is correct, we would get a sort of a drying equivalent BUI of the highest values ever recorded in Jasper, up to about 200. Again, there is a lot of weather data to look at. I'm not going to go over too much here, but just to show at the time of ignition, the station closest to the ignition points had about FFMC, close to 96. And the BUI of about 150. And then with the max winds during the convective event, that would lead to an effective, maximum ISI of about 28. So, very significant fire weather at the time of ignition. But then you can see there's some rain in all the stations that night, which is interesting. Some of the stations were north of the fire, some of them were south of the fire, and those caught rain. However, the one alpine station, which isn't shown here, from Marmot, which was just west of the fire, took no rain during that event. And that one was arguably the closest, although much higher in elevation. So this was a real head scratcher. We don't believe there's any signs that the fire took significant precipitation during that time. But of course, the precipitation affected the weather stations and probably affected some of the fuels in the vicinity. So it's although there's a great weather network, it's not that clear to sort it all out. And finally, if you doubt individual weather stations, it's always useful to look at weather models. So this is the HRDPS modeled winds at the head of the fire, extracted at several points during the fire spread. And this is winds at different elevations. And so the lowest arrows show the ground level modeled winds. And there's a reference arrow showing 50 kilometers an hour in the lower left of this graph. So just like the weather stations showed, at the surface level, as this fire progressed, the surface level winds were generally very low, below 10 kilometers an hour, with the exception of in the immediate vicinity of the plume, the fire generated winds, which were extreme. And finally, I noted, many of us are familiar with using the online tools to access imaging and hotspot data. And so this is just kind of a snapshot of some of the VIIRS imagery. And, this is some beautiful images in the first, the main day, the 23rd, and the night of the 22nd of both the South Fire and the North Fire on the left. However, as the fire reached near Jasper, unfortunately, this cloud band, together with the smoke in the air, basically blocked the satellite imagery from hotspot detections. And so, there's no doubt the fire reached the town site, but it didn't show up in this imagery. And there's some evidence of the overnight on the 23rd, 24th, but very little as the fire actually entered the Jasper town site. So that made reconstruction much more difficult. We had to use a lot of direct observation and anecdotal evidence. And finally, rate of spread modeling here. So this just shows a whole bunch of FBP and FBP related rate of spread models, fitted to the initial spread index, and along with 4 direct, monoplotted or high resolution reconstructed observations of the fire spread on the 24th. And as you can see here, the C3 model is the bottom black line, which we believe in the absence of the mountain pine beetle would have best represented this area. Of course, the actual observed spread was many times higher than that predicted by that model. And there's other models here from the FPP system, including the C2. And then at the top, there's the M3 with 100% dead fir, as well as a sort of custom unpublished model from the International Crown Fire Modeling Experiment. And those two models are somewhat closer, but still, would have underpredicted fairly significantly the fastest spread. So again, this is just the challenge with some of these tools, which assume wind-driven fires and assume that 10-meter open winds do a good job of representing the main wind force affecting the fire. And this was clearly a plume-driven fire, and so these tools did not do a very good job representing rate of spread. And finally, the head fire intensity here, which again is rate of spread multiplied by a constant multiplied by the mass of fuel consumed. And so this gives values of 100 to over 200,000 kilowatts per meter. So some very, very high values, and also suggests that flame lengths, these models are not perfect. There's some issues with these crown fire flame length models, but nonetheless, are indeed expected to be very high from this event. So finally, the main influencing factors we believe were drought, continuous conifer fuels, the mountain pine beetle mortality, multiple ignitions with gusty winds, plume-driven behavior, and the column collapse event. There's a lot of uncertainty around wind speed and plume dynamics, particularly combined with the mountainous terrain and different elevations. As Luke Collins will describe in more detail, this was an example of the wildfire disaster sequence, where multiple starts and rapid growth quickly overwhelm any suppression capacity. So we suggest resilience in these landscapes will require a combination of community risk assessment and planning, appropriately situated and maintained fuel treatments, fire-resistant structures, and community preparedness, all tailored to local settings and with local community buy-in and cooperation. And finally, unfortunately, the impacts of fire reach beyond data, models, and science. First responders and support staff came together under extremely dire circumstances to protect the lives and homes and livelihoods of Jasper and the national park. So we dedicate our work in this report that the CFS put a lot of work into to the memory of Alberta firefighter Morgan Kitchen and his family and the members of his fire crew from Rocky Mountain House, Alberta. Morgan died on August 3rd, 2024 during operations on the South Fire. This was a few days after the damage to Jasper had occurred. And highlights the continuous danger first responders face in modern fire environments. So we hope his sacrifice will be remembered. And so this was the report that came out about 3 weeks ago. If anyone wants the links, we can provide it. You can find it on ResearchGate. Some of the authors posted it, and it's also available on the Canadian Forest Service library. And so there's the link for anyone who wants to capture that from the video later. And so this was a real effort from several of us from across the country to come together and put this. And I'll give a shout out to my friend and colleague, Dan Thompson, who was the original project leader, but had to hand it off due to a family emergency. So thanks very much. And I will now hand it over to Luke.
All right. Thanks, everyone, for attending today. It's great to see such a large turnout. So today I'm going to be discussing some of the work that I did with Brandon McKinnon that was examining the effects of the characteristics of the built environment on the urban conflagration that occurred in Jasper, in the townsite of Jasper. And the reason why, the main reason why Brandon and I were really interested in this is because urban conflagrations are associated with some of the most devastating impacts to communities. And understanding what factors are influential in their initiation and development will be really critical for, identifying effective risk mitigation strategies. Unfortunately, Brandon can't make it today because he's on vacation. That's probably fortunate for him, but unfortunate for everyone here. So I'll be presenting this work solo, but I just want to, emphasize that this was really a collaborative effort. I assume that there are a few people on this call that are residents of Jasper and have experienced the impact of this tragedy directly. I'm sure the past 12 months have been very challenging, and I really hope that you're all doing okay and are in a good place given the circumstances. In preparing the talk, I've really tried to minimize the use of imagery that is depicting community impacts. But there are a few slides here and there where I've had to use them just to illustrate points. So I really hope that these images aren't triggering for anyone on the call. Before I start, I just want to acknowledge that the work that I'm presenting today is just a component of this larger report that is examining the community impacts that resulted from the Jasper wildfire. There is a lot of interesting data in this report. There's some interesting findings. I kind of felt it was just too much to do justice in a 25 or 30-minute talk. So I've decided today just focus on what some of these key results and findings can teach us about understanding the factors that were contributing to the initiation and spread of the urban conflagration, and what some potential mitigation strategies might be moving forward. This slide's just giving a little bit of an overview of the key events that occurred in the sequence of the development of the urban conflagration at Jasper. So as Dan mentioned, there was some pretty extreme fire behavior that prevented effective containment of the fire in the wildland. When the fire impacted the community, it was through this initial exposure to an ember shower, and this was most likely associated, as Dan mentioned, associated with the collapse of the convective column. Observations from firefighters present in the town site identified structures with wooden roofs as being among the first that were to ignite. And then following, these initial ignitions, the development of structure-to-structure fire spread occurred. And this really escalated the growth of the urban conflagration. And, within about a 24-hour period, there were roughly 300 houses destroyed in the southern end of Jasper, along with many other institutional and ancillary buildings. And you can see in the map of structure destruction here that there's a high degree of clustering of houses that were destroyed. And this is really indicative of that structure-to-structure spread of fire that is characteristic of urban conflagrations. Now, the sequence of events that occurred in Jasper share many similarities to other urban conflagrations. And this has been really nicely summarized by David Colkin and colleagues in their model describing the urban fire disaster sequence. And Dan touched on this at the end of his talk. So the disaster sequence starts when wildfires ignite and burn under really severe weather conditions, resulting in fire growth and fire behavior that essentially overwhelms available suppression resources. Now, if these fires ignite at the wildland-urban interface or if these fires ignite in the urban interface or spread to the interface, they can expose many structures to either direct flame contact, high radiant heat loads, or a lot of embers. And this can lead to the ignition of many structures at the same time. And if the number of structures that are ignited exceed the suppression capacity of structure protection crews, this is when you have a high potential for an urban conflagration to develop. In situations where you have a lot of structures that are located in very close proximity to one another, so there's very small spacing between structures, fire can very easily spread from structure to structure. And this is where we tend to see the greatest impacts and the greatest losses of structures. So this is what happened in events like Fort McMurray, Slave Lake, Jasper, and the Los Angeles fires that occurred earlier this year. The alternative pathway, which is the pathway on the bottom, occurs when you have many ignition-resistant structures in the community. And as a result, only a few structures might ignite. Structure protection resources are sufficient to contain the fire spread within the urban environment, and you avoid the development of an urban conflagration. So the work that I'm presenting today is really trying to assess two aims related to this topic. So the first is we're trying to understand how the community conditions were influencing structural loss rates across neighborhoods, with the purpose of trying to identify some of the aspects of the built environment that were facilitating the initiation and spread of the conflagration. The second aim of this work is to, which I'll talk about later on, is to identify some of the potential, characteristics of the urban environment that might point to things that we can do to mitigate the likelihood of fire initiation due to wildfire, as well as the structure-to-structure spread of fire once initiation occurs. So starting with this first aim, we really focused on the patterns of structure losses at the neighborhood scale. So we defined a whole range of different neighborhoods within the southern end of the Jasper town site that was exposed to that ember shower. They're depicted by the black polygons. And for each one of these neighborhoods, we quantified the proportion of houses that were destroyed within the neighborhood. And then we characterized the urban environment using 3 different metrics that were potentially related to either the initiation of fire or the spread of fire within a neighborhood. And they were the proportion of combustible roofs present within a neighborhood, the amount of woody vegetation cover in the intermediate structure zone of houses, so that's the area within 10 meters of a house, and the spacing between neighbors. So we looked at the minimum spacing between a house and its closest neighboring structure. And we quantified these 3 variables at the neighborhood scale. We then ran multiple regression analysis to try to understand what the relative effect of each of these was on the patterns in structure loss across neighborhoods. And what we found was that combustible roofs were the most influential variable, followed by woody vegetation cover and structure spacing. So the plots on the right-hand side of the screen showing the effect of the predictor variable. In this case, it's combustible roofs, so it's on the x-axis, on the rate or proportion of houses that were destroyed within a neighborhood, and that's on the y-axis. The gray lines showing the predicted the predicted proportion of houses destroyed, and the gray polygon shows the 95% confidence intervals. And as you can see, with every 10% increase in combustible roofs present within a neighborhood, there was about a 30 to 40% increase in house loss rates. So a simple way of thinking of this is that for every combustible roof you added to a neighborhood, an additional 3 homes were being destroyed. So this is really indicating that the presence of these combustible roofs within a neighborhood is really having a disproportionate influence on the risk of house loss. We looked at the vulnerability of houses with combustible roofs to ignition and destruction when they were exposed. So we found that 90% of exposed houses with combustible roofs were destroyed. This was compared to about a 50% loss rate for structures or houses with ignition-resistant roofs. We also looked at clusters of destroyed and surviving houses within these neighborhoods. So, this is basically groups of destroyed houses and groups of surviving houses. And we wanted to sort of see whether they differed in terms of the occurrence or proportion of combustible roofs present within the cluster. And we found that 75% of the destroyed clusters contained at least 1 combustible roof, while only 20% of the surviving clusters contained a combustible roof. So when we consider this, evidence with the observations from firefighters present on the ground, which reported that, these combustible roofs were among the first to ignite, we see a pretty strong case that these houses were facilitating the entry of fire into some of these neighborhoods and are really promoting that initial spread of fire by impacting their neighboring structures. For woody vegetation cover, we saw a pretty similar relationship. So with every 10% increase in woody vegetation, there was about a 25% increase in loss rate. Something to note when interpreting the plot that I've presented here is that I've presented these predictions across the full range of cover values that were present across Jasper, but you'll notice there's one outlier at around like 38% cover. The reality is that most of the neighborhoods within Jasper were within about 10 to 25% woody vegetation cover. So I just wanted to point that out because the magnitude of change in this graph looks very extreme, but the reality is that it was operating over a much smaller range generally of woody vegetation cover values. So in terms of woody vegetation cover, we think it was potentially contributing to house loss rates by either facilitating ignition within neighborhoods, facilitating the spread between structures, or influencing the intensity of fire close to structures. But we don't really have any conclusive evidence that points towards one of these things or all of these things as being a dominant driver. For structure spacing, we found that the opposite relationship. So as you increase the spacing between structures and their closest neighbor, you reduced the proportion of houses that were destroyed within a neighborhood. So if you increase the median spacing from, say, 2 meters to 6 meters, there'd be about a 25% reduction in loss rates. Now, we felt that this effect, or the effect size of structure spacing, was a little bit smaller than what we had anticipated, because we know that structure spacing is really key for promoting structure-to-structure fire spread. So we examined the effect that proximity to burn structures were having on the survival or loss of individual houses. And what we found was that for houses that were located within 5 meters of a burnt neighboring structure, it was almost certain that they'd be destroyed. Whereas those houses that were located 10 or 15 meters or more away from a burnt neighbor had a very high likelihood of survival. So what this is really pointing to is that structure-to-structure spread was highly likely when there was less than 5 meters spacing between neighbors. We looked at the distribution of structure spacing across the Jasper townsite, and we found that about 90% of houses were within 5 meters of a neighboring structure. So this is really indicating that the way that the buildings were arranged within Jasper, this close structure spacing, really was conducive to the promotion of structure-to-structure fire spread once an ignition occurred within the neighborhood. And this really explains why we're seeing a small effect of structure spacing in the previous analyses, and the dominance of say, wooden roofs or combustible roofs and woody vegetation cover in determining the patterns in structure loss rates. Basically, all the neighborhoods had structure spacing that was conducive to structure spread. So now moving on to the second aim of the talk. We really wanted to try to understand what characteristics of the home or the property surrounding the home were effective at either preventing the initiation of fire within the urban area, so preventing those first ignitions due to exposure to the wildfire. And then secondly, if a fire was to ignite within an urban area, are there any ways that we can design houses or manage vegetation to break that structure-to-structure spread of fire? So, as you know, all of you probably know, there are many ways in which structures can be ignited when exposed to wildfire. It really depends on where the vulnerabilities are located and how the structure's exposed. Ember ignition of wooden roofs is just one of those mechanisms. So we wanted to really assess a broader range of factors that were causing ignition of structures by wildfire across the entirety of the Jasper wildfire. And we did this by undertaking post-fire field investigations at locations located outside of the town site. So we wanted to target these locations because there was less influence of structure-to-structure fire spread, and it was just easier to kind of attribute certain ignition pathways to the destruction of houses based on that evidence being retained around the house. I just want to acknowledge that Brandon and Robin Tremblay were the two people who did a lot of this work, and the analysis of this data and interpretation is Brandon's. This is really his area of expertise, and I'm just hoping that I can do it justice. So many of the sites that they investigated consisted of cabins or lodges containing structures that were really almost identical in terms of their design and landscaping. And this was a real bonus because it helped determine what the pre-fire characteristics were for many of the destroyed structures. Because as you can imagine, when a structure's been destroyed, it can be challenging to figure out what it looked like before the fire. So the way that structures were sampled within these locations was a paired design. So there were post-fire field assessments on pairs of burned and unburned structures. There was also, where available, the investigation of partially impacted structures as well. The methodology involves structure assessments using a mobile application, which was a Firesmart app that allowed an assessor to document structure characteristics in a pretty repeatable and systematic way that started from the roof of the structure, worked its way down to the base of the structure, and then out through the home ignition zone. Qualitative assessments and investigative techniques were also used to identify potential exposure and ignition pathways. So across the 8 locations that were investigated, there are a number of common traits that were associated with the destroyed structures that we think were likely contributors to their ignition. And these were combustible roofing materials, the presence of continuous pathways of fuels up to the structure. So the photos on the bottom of this slide here, hopefully you can see my mouse, provide an example of that. So the destroyed structure in the foreground had continuous wildland fuels leading up to 3 of the 4 sides. The paired surviving structure, on the other hand, had a number of non-combustible fuel breaks surrounding the structure. It had several meters of defensible space between the wildland and the structure itself. And this likely reduced the level of exposure from radiant heat and prevented that direct flame contact occurring against some of these vulnerabilities that were present, like the combustible decking material. Another factor that was important was the presence of combustible materials near and at the base of structures. So one common theme here was the presence of mulch beds at the base of structures, and this can be particularly influential when they're located at the base of, say, combustible siding. Combustible materials under and around decks were another characteristic, as well as long dead grass and other fuels leading up to a combustible surface, so things like combustible siding and combustible decks. So these findings really emphasize that, by following some of the principles outlined by Firesmart, we can really reduce the risk of structure being ignited through wildfire exposure, and we can kind of prevent that initiation of or minimize the likelihood of initiation of this urban fire disaster sequence. When an urban fire starts, characteristics of the structures themselves may be influential in breaking the structure-to-structure spread. We're really interested to see whether we can find any evidence of this. So for this work, we looked at pairs of structures within the townsite. So it was a destroyed and surviving pair. We located these pairs at the end of a row of destroyed structures. So we would sample the last destroyed house in the row and then the first surviving house. And essentially all we're trying to do is understand, were there things that were different about that surviving house compared to the destroyed house? And using that same assessment protocol, we assessed characteristics of the buildings in terms of their resistance, ignition zone fuels, and we also included information about their exposure, so that the proximity to a burnt neighboring structure. For this analysis, we looked at it we analyzed this data in a number of different ways. I'm just going to present one of these sets of results, whereby I've compiled the building resistance and ignition zone resistance data into a composite index. So a value of 1 would indicate a very ignition resistant building or ignition zone. A value of -1 would represent a vulnerable building or ignition zone. And what we found was that surviving structures were not any more resistant than destroyed structures. There was no real difference in their building resistance. We found that surviving structures were scored as having more hazardous fuel in the ignition zone than destroyed structures, but we're certain that this is an artifact of the methodology. So as you can imagine, when you're looking at a destroyed structure, it's a lot easier to assign it a low hazard score because a lot of the fuel hazard has been consumed around the structure. So pretty sure that this result is an artifact of a bias in the sampling methodology. One thing that was apparent was that the surviving structures had a lower exposure to burnt neighbors, so they tend to be further away. So around about 50% of the surviving structures were located 5 meters or further than a burnt neighbor. About 80% of the destroyed structures were within 5 meters. So what this is really suggesting is that building materials and landscaping are having really little influence on house survival when structure-to-structure fire spread is occurring. And this is really consistent with other studies that have been conducted elsewhere and some work that we're doing within the Canadian context. A couple of things to note. Small sample size. There's only 15 pairs used, and there's a lot of uncertainty in the collection of this data because you're trying to piece together the information from destroyed structures. And, you know, we had a few different surveyors collecting this data, so there was definitely some variation in terms of the expertise of surveyors. The other factor that was apparent, and I think someone just posted this as a question, was the effect of suppression. So we noted that within a number of these pairs, there was demolition, there was mechanical demolition of the burnt structure was evident. So essentially that burnt structure, that last burnt structure in the row, once it ignited, had been demolished, and that was done to save the other unburnt structures within the neighborhood. So there was definitely evidence of suppression intervention. And following on that theme, I just want to end by saying that, you know, we weren't able to statistically assess the influence of structure protection because it's really hard to sort of come up with one or two metrics that kind of quantify all these different actions that are taking place across the fire. So it's just not possible for us to include any information about that in our models. However, we know that there were substantial structure protection efforts that occurred. You know, there were hundreds of firefighters present. Kilometers of sprinkler lines were established along the wildland urban interface before the fire impacted the town site. Structural protection crews were going through and removing ignitable materials from around structures. So there's an example of this in the photo on the bottom left here. You can see, you know, we've got piles of firewood, lawn furniture, gas tanks, gas bottles that have been removed from around the house to you know, reduce the likelihood of ignition. There was plenty of evidence where suppression had been effective at you know, suppressing vegetative fires as well as structural fires. So the photo bottom center here shows one of the commercial buildings where the shake roof had ignited, but structure protection crews were able to suppress this fire before it, you know, completely consumed both itself and neighboring buildings. And as I mentioned in the previous slide, demolition of structures was effective in breaking structure-to-structure spread. We also saw evidence, you know, and homes where sprinklers had been deployed and appeared to have been effective at, you know, protecting or making the home ignition zone less ignitable. It's kind of tricky to disentangle, you know, these lawns were also very well maintained, so it's kind of hard to disentangle whether that was the effect of the sprinkler being present during the exposure event or because the frequent use of sprinklers had just made the home ignition zone less ignitable. But, you know, the point is that there was lots of evidence that suppression actions were working. So just wrapping up, how can we reduce, what does this tell us in terms of how we can, the things we can do to reduce the risk of future urban conflagrations? So, you know, from this Jasper case study, it's clear that, you know, retrofitting combustible roofs will be a really effective way at reducing the vulnerability or the risk of urban fire initiation. But as we pointed out, there are plenty of other vulnerabilities present on houses will also need to be addressed. Ignition-resistant landscaping adjacent to structures, especially where there are vulnerabilities present on the structure, will be important. As well as managing hazardous vegetation in the structure ignition zone. And I just want to note that, you know, the municipality of Jasper have made several changes to the development policies to address these issues or start addressing these issues. and this includes prohibiting the use of wood siding and roofing on structures. There's now a requirement for a 1.5 meter non-flammable buffer around new homes. Any wooden structures, attachments like fences or decks need to be at least 1.5 meters from structures. If they're within that 1.5 meter area, they need to be constructed from non-combustible materials or have a non-combustible, non-flammable coating. And then finally, any new coniferous trees that are planted need to be more than 10 meters from a building. Another sort of key finding from this work, which doesn't apply necessarily to existing communities, but new developments, it might be wise to create sufficient spacing between structures to mitigate or reduce the likelihood of structure to structure fire spread occurring. So our results suggested that if you have 10 meters or more spacing between structures, that should be a pretty effective distance. This won't be practical or achievable in all communities, particularly where there are housing shortages, but it's just something that could be considered. And I think the key point in communities like Jasper, where there's very densely built up urban area, preventing the initiation of the urban fire is going to be critical. And this is really going to require ongoing actions. And as our results point out, this needs to occur at the community scale, because the presence of one vulnerable structure within a neighborhood can really reduce the resistance of all structures and increase the risk to all structures across the neighborhood. So, yeah. And just before I wrap up, I just want to acknowledge some substantial contributions from Robin Tremblay from FPInnovations and Natalie Maslowski from the Canadian Forest Service, who both spent a lot of time doing some of these field data collection. There was also a host of other people that contributed along the way. Akira Hartley-Nakao helped with the preparation of a lot of the spatial data layers and trying to get the the Firesmart app data into a format that was suitable for analysis. Parks Canada provided funding to FPI to do this study and produce a report, and we're really appreciative of that. They also provided a lot of data and expertise, as did the municipality of Jasper. And then finally, thanks to the many firefighters and people who are present within Jasper who were willing to share their knowledge and experiences, because it really helped us to be able to piece together the most accurate depiction of events that was possible. So yeah, just wrap up there, and I guess we're ready to take questions.
Awesome. Thank you, Daniel, and thank you, Luke. Those are great presentations with a lot of information, but really well summarized. And I like that you both kind of focused on those key take-home messages. So I appreciate that. We have some questions already popping up in the chat. And just so everyone's aware, you can post your questions in the chat box. If you would like to ask your question yourself, you are welcome to raise your hand and I will call on you. But just to let you know, it is being recorded. So if you do that, you will be included in the recording for this session. So the first question, I believe, goes to you, Luke. And there's a question around whether you were able to categorize combustible roofs. So assuming the predictors were based on what you were able to interpret from pre-fire imagery.
So we were really fortunate that the municipality of Jasper actually surveys their roofs and identifies potentially combustible roofs pretty much annually as part of their, I think it's part of their fire risk mitigation strategy. So understanding where potential vulnerabilities lie within the community. So for the combustible roofs, the level of detail that we got essentially was it a wooden roof or was it old degraded asphalt? So we essentially were lumping them into that kind of binary category of combustible and non-combustible. Yeah, so we weren't able to look at degrees of combustibility within that, but that would be very interesting if you could come up with a metric that describes that.
Thanks. I imagine that this next question probably has a similar answer. But there was curiosity around with combustible roofs being the leading determinant of burn structures and overwhelming suppression responses. Do you think it might be possible to model how removing that variable, so taking out the combustible roofs, may have changed the suppression response on other structures? So it's
Yeah,
more of a hypothetical.
yeah, this didn't make it into the report, but just being curious, I looked at fitting the model that was developed using the existing distribution of combustible roofs, and then see what the loss rates were, and then by taking them out and then seeing what the loss rates were. And this is like a back of the envelope calculation, so I don't take it with a grain of salt, but if I recall correctly, it was a substantial reduction in loss rates. So like I want to say about 75% reduction in loss rates if you were to take them out and refit, and predict with the model that had been fitted on that original data. But there are a lot of caveats to that approach. So
yeah, I imagine suppression is a huge caveat to that resource availability, but I would assume that reduction would be from the initial ember fallout, not being able to start those ignitions and start that chain reaction of structure to structure sequence to begin with, right?
yeah, I mean, my understanding was that like things happen so quickly, and there are a lot of other factors, like visibility was really bad in the town site. So once you get many structures igniting at the same time, like it's would be extremely challenging to manage that scenario. So one of the key things, though, once those combustible roofs ignite, they themselves can produce a lot of coarse embers, which can then expose neighboring structures. So yeah, I think I think it's very challenging thing to sort of pick out whether it was the ember shower or lack of whatever, not having the suppression resources there.
Thanks, Luke. Dan, I have a question here for you, or I guess for both of you. Are there estimates on ember transport distances from the fire itself? And can you comment on the fire vortex or pyroCbs?
Right. So I think some of these things, we had a lot of discussions within our group, about what we thought there was strong evidence for and what made it into the report, and hopefully what I was able to say in the presentation versus what we could maybe speculate to, but really couldn't really provide evidence for. And ember transport was unfortunately one of the latter. So we had various ideas about embers coming from high subalpine slopes and going, a kilometer or more. And then there was also some riparian areas, much closer to town that some people thought might have been the source of some embers. So essentially, we don't know. However, there was this column collapse, and that appears to have, at least been partly linked to high subalpine slopes and the sudden loss of fuel as the fire, ran out of fuel going up the ridge of Whistler's Mountain and some of the surrounding mountains. And that's not, right beside Jasper. That's a couple kilometers away from the town site. But then there was also an effort by some of the field team to go out and look for evidence of embers on things like tarps and other materials. And it's hard to do an extensive search. In some of the areas they searched, they actually didn't find extensive ember shower evidence. And so, one of the initial hypotheses was that this maybe was less of an ember driven event. And it wasn't until we sort of put the data together with Luke and Brandon's work that it became evident that, there wasn't a lot of sort of fire spread from, surface fire or crown fire spread, from across all these roads, going in. It clearly was an ember ignition event, mostly that led to the structure ignitions. So yeah, I could speculate beyond that, but I think that sort of the sum is we don't know, and we can't really quantify the ember distances very well.
Thank you. I was wondering if I have my own question, then I'll get back to the group questions, but I was wondering if you could each speak to how quickly task teams were assembled, deployed, and on site to be able to make these reports possible and gather the evidence.
Well, it wasn't instant. We don't have teams on standby for this type of work. So the Canadian Forest Service does have a WIPS, or Wildfire Intelligence and Predictive Services unit, that does a lot of operational response, but often it's remote work with doing modeling and providing data and analyses. There are deployments, but they take a few days. So I believe roughly it was about July 29th or 30th that we received the request from Parks Canada. And then it took about 2 to 3 days for the first members of our team to arrive on site. So it, we weren't there in an hour or anything, but it also wasn't weeks. So that helps. And I'm not sure, Luke, if you wanted to comment for your team.
That sounds consistent with my answer.
It's still pretty quick. I thought it was quite impressive when I had heard from some of the people who were involved in the task team. So I want your attention to that, because it's not an easy feat, and to have that, it's a testament to the coordination to be able to go in there with methodology already and some ideas of how you're going to gather this stuff. And I think we'll only get better at it with time, right? So
Yeah,
good job.
I can comment on that a little bit on Brandon's behalf. So FPInnovations are actually working at, like, one of the challenges we had, we felt like we were scrambling when we came to Jasper, because we didn't have enough time to really think about like the methodology, etc. But as part of a wildland resilience future initiative project, FPI are actually working at developing a protocol for getting approvals to go to these events, a data collection protocol and data sampling protocol. So there's definitely work, and there are definitely work going on to help improve our speed, or speed up this process, so that we're collecting the best data in the shortest amount of time.
Thanks. Sounds like a great project, and I think it'll be useful across Canada. So great initiative there. Dan, I'm going to send you another question here. Just curiosity around whether you could comment on the column collapse and the role of the cold front on the fire.
Right. So some people did suggest that there was a cold front passage, and then we had some some meteorology specialists among our team, and discussed sort of some of the data, and I think the conclusion was that it did not meet the definition of a technical cold front, but there was something that appeared to be a micro front or a mini front that some people thought passed, and again, it's we're kind of into the realm of speculation. There was a lot of forces interacting at the time between the fire itself, these sort of sudden arrival of the fire to this major valley confluence, right? Of course, the municipality, the Jasper townsite, is right at the confluence of the Mayette, the Yellowhead Pass area from the west, the big valley to the west, as well as the Athabasca, and then there was the fire generating all this intense energy, and as it sort of raced up the slopes, there's also ignition operations going on, trying to steer the fire away from values, and so yeah. There may be some research models that could sort of compare various factors quantitatively. I don't know how valid those would be either, but we weren't really able to say too much more, except that a column collapse was observed. It appeared to be as the fire, raced up this slope and ran out of fuel, and there was also these a bit of an increase in wind speed from the weather stations around that time, but nothing that would suggest a major wind event or anything. And then, as I noted, a few hours later, there was significant rains in the area, so there's clearly a weather system coming in, but it did not appear to be anything that would be considered a major cold front.
Thank you for that clarification. Luke, are you aware of any information on roof slope shedding? I got to read this one again. Apparently I didn't have enough coffee. Are you aware of any information of roof slope shedding flaming embers, such as A-frames, preventing snow buildup?
Yeah, that's a really good question, and I mean, I've definitely seen the complexity of the roof shape and design as being a factor that's suspected to increase the vulnerability of ignition. I don't think I've seen any quantitative, like empirical research that has actually demonstrated that. It's not the A-frame roof style, but we've been looking at like whether the complexity of roofs, like whether they're layered or whether they have many yeah, sort of bends in the roof, whether that's actually increasing the vulnerability of structures to being destroyed in other fires that have occurred in Canada, but we're not seeing, you know, a strong influence there. So I would assume that it could help, but I can't say with any certainty.
Yeah, it's an interesting one. You think, some of the roofs that you see, especially on the fancy commercial buildings, they've got, A-close and potential catchment areas. But
Yeah.
yeah, it's
Yeah,
an interesting question.
it's an interesting, like, yeah, like it, the shape of the roof, like, yeah, it could potentially help shed the embers, but it increases the surface area. So, and then you potentially have a gutter at the, you might have a gutter, I guess, at the base of some of those roofs. And then like, it's just, yeah, it's pretty complex trying to, identify the effect of those specific features. Because there's also often a lot of other vulnerabilities that are associated with a structure like that.
Thank you. Sorry if you could see me laughing. I'm getting comments on my inability to read properly without tongue twisting everything. Okay, I'm going to bring it back to you, Dan. Can you elaborate on ignition spread and subalpine above the treatment areas? So how that may have contributed and implications around what should be a treatment area candidate?
Yeah, that's a really good question. I mean, if you're into fuels and fuels management, that's an excellent question, right? Parks Canada had done a tremendous amount of work. Good for them, right? They were pioneers in the early 2000s of doing fuel treatments around their their town site. Evidence suggests it did help with suppression in the immediate vicinity. It did help with reducing crown fire, occurrence and involvement, as I noted. But it clearly wasn't enough to reduce a significant amount of damage. I guess if I had to bring my own bias to this, I think Park Canada is on the right track with an extensive prescribed fire program. But obviously it's unpopular and there's a certain amount of risk to prescribed fire very close to values. So I think that's sort of where we landed with our final management recommendations, that there wasn't any one solution that would be able to be a silver bullet to completely eliminating the risk of this type of event in these landscapes. But many things can help. And so we had sort of something we might characterize as a glancing blow. It still caused a lot of damage, but without any of the management, the fuels management, maybe even the controlled ignitions during the fire and the extensive urban firefighting as well. It could have been much worse. That's again speculation a little bit, but I think there's some other papers coming out from the US suggesting very significant effects of prescribed fire on reducing fire severity in large fires. So I think there's a number of techniques. Mechanical treatments can be good, but they're potentially expensive. And they also require maintenance, and they don't deal with the surface fuels necessarily. So prescribed fire has its risks, it has its problems, can cause a lot of mortality, and also needs to be repeated and smoke and all this sort of thing, but it has other advantages. So yeah, probably just should stop talking about this. I think there's lots of pros and cons, and any individual project needs to be sort of evaluated on its own merits.
Thank you. And I'm glad that you brought up the prescribed fire program. I feel like we're talking a lot, we being the larger wildfire community, but also municipalities and the general public, about accepting a changing fire world and changing climate and changing circumstances around that. And I think we talk a lot about changes to suppression and expectations for suppression. But I think we need to talk more about changes of expectations and acceptance of things like prescribed fire use, and that there needs to be a certain amount of acceptable potential failure to it as well. It is something that involves risk, but everything in life does, and we need to be more open to use of fire, whether it's cultural, traditional burning, prescribed fire on the land, and realizing that it's also not going to be perfect 100% of the time as well. So things like smoke are a part of it. Things like fires getting out of control are a part of it, but we're taking it to reduce the overall risk in the long run. So I appreciate you bringing that up.
I think you also touch on a really important point, and that is that like no one action is going to be 100% effective, and really addressing this issue of impacts on the community is going to require a holistic approach. So it'll be a combination of, you know, field treatments as well as hardening of structures and flammable materials in the urban environment, and having sufficient suppression resources given, you know, the circumstances. So I think, yeah, it's like, I don't know, I feel like there was a lot of focus early on about the fuels, but I think it's a really complex management situation, particularly in a place like Jasper. And yeah, I think, you know, focusing on the bigger picture, you know, what are the multiple strategies that we can do to reduce the risk is a, you know, the approach that needs to be taken.
I agree with what both of you said. So yeah, thanks for that nice discussion.
Thanks. Yeah, and community involvement and buy-in is such a big part of it. And I feel very fortunate to have spent a little bit of time in Jasper this spring. And as part of that, through the Canada Wildfire Research Strategic Network, we hosted a kind of live science nerd night where we brought in some researchers. They didn't talk about the fire specifically, but about other research going on within the park. And I have to say, I was just so impressed with the community there and their open-mindedness and involvement and real ownership of not just the town site itself, but the park as a whole. So I think there's some great examples of where this is working well and it can still be improved upon, but I don't want to make it sound like there's, you know, only ways to get better. There are good things happening, and I think we can build upon those. So there's a question about whether or not the Firesmart app is available for homeowners to use for self-assessing their homes and neighborhoods. I don't know if this is something.
I do not know. You could contact people from Firesmart Canada about that. So I think Ray Alt is one of the contacts there. Yeah, I'm not sure. I assume it's publicly available, but I can't say for certain.
I probably should know, but I don't either. If anyone in our group here knows, please let us know in the chat. Otherwise, Firesmart Canada has a great website, and yeah, Ray Alt would be the chief person to go to for that question. So that is all of the questions so far in the chat. If anyone has any extra ones and wants to put them in there, feel free to, or if you'd like to pose your question live, feel free to raise your hand. I will go back to my questions in the meantime. Oh, thank you. One of our people posted a link to the app in the chat. And yes, it is. Brand new updated version available. Firesmart Begins at Home app. So thank you. Thank you to the masses. Okay, so I had some questions around the kind of 5 to 10 meter spacing between structures as being a real, it seemed like a real line in the sand for that structure to structure spread. And I was curious, you think of a large urban community and we're kind of going the opposite of that. We're looking at infill and increasing density and how suburbs and sprawl, and it tends to use the opposite language. But I was thinking more and more about kind of those places outside of the large urban. So whether you're looking at, you know, cottage country, those places that might not have huge resourcing available as well for structural protection. And I wonder if there would be interest or support from groups like insurance companies or things to be kind of doing this kind of work. I guess I don't really have a question. I was just curious if you knew if there was any discussion around it, or if it's been something that's kind of been tabled at the municipal level, or if it's a relatively new finding from this report.
I don't, I guess it's not a new finding per se, if you look at it in the global context. Like similar, you know, spacing distances have been reported from work in like California and other fires in the US. I'm not sure, you know, as you mentioned, like there's this real challenge, right? We've got housing shortages, and places like Jasper where, you know, you're really constrained in terms of expansion of the urban area. It's really challenging to implement those kind of spacing requirements. So, you know, I'm not actually sure whether you know, there is any action in that regard. I'm assuming, it's probably not a desirable thing from the perspective of a developer because, it means obviously less money, but yeah, I'm not sure. I kind of wonder though whether there are ways that you can artificially create that spacing by like having houses offset on blocks. So, like some houses closer to the road, others set back a little bit more. Maybe that's a smart way that you could do it while still maintaining housing density. Yeah.
Yeah, I think that's a great suggestion. I was thinking I live in an old 1970s bungalow neighborhood where we have fairly large lots, and we almost have that by nature. I have one of those unfortunate houses where it's really far back on the lot. So I have
Mhm.
all this wonderful front yard space and not enough room for my kids to run around the back. And then there's others that are front. But then when I go into the new communities, it's long, narrow,
Mhm.
and nearly touching each other. And I kind of was wondering if even just a switch of the directionality of those lots
Yeah.
might be a win.
I mean, another thing could be like implementing green space within the neighborhood, so you're not getting it between every structure, but having like a playground or whatever, just to break up the neighborhood so that it kind of can potentially aid in the containment. Maybe that's helpful. It'd probably be good to get to talk to some people who are involved with like suppression activities in terms of whether that's actually useful or whether it's just better to go in there and just demolish like sacrifice a house to save the other houses in the neighborhood.
Mhm.
Yeah.
Yeah, those that brings in a whole nother social dynamic to it though, because often it's people from community having to make those decisions.
Hmm.
And there have been documented cases of people having to choose to demolish their own place, which is quite
That's right.
sad. But I was going to switch one more question back to Dan before we wrap up here in about 8 minutes. I was curious if you could talk a bit more about the wind speeds that you were able to, I believe you said you were able to kind of back calculate some of the maximum wind speeds from the actual event. And if you could talk, I don't know if you have any pictures that you could go back to, but some of the really interesting kind of blowdown or uprooting or breaking of trees. I'm thinking kind of like below the Marma Basin area, there was some really interesting patterns that were showing up. If you could speak a little bit to that.
Yeah, for sure. There was some real violence going on there for sure. I guess our report, some of this, maybe I don't know if some of the co-authors want to speak up here if or write comments in the chat. They were, some like Dan Thompson or if Ginny is on here, who were a little more involved in these calculations, but there was some estimates. We had this intense ground scouring, essentially sand blasting, observed of tree boles, whether standing or on the ground. I mentioned some of the built materials that were lofted several hundred meters. There was a dumpster, a big steel dumpster that was lifted and dropped in the Athabasca River and had to be retrieved. So the sort of tornado force winds on the EF scale of about 4 to 5. These are events typically of sort of 200 to 250 kilometer an hour winds. So this is just wild, right? Because I mentioned winds of less than 10 kilometers an hour at the weather stations, and at the same time near the fire front, there's this maelstrom, if you like, this incredible tornado type event going on. And burning at the same time, of course. So what a huge amount of energy was released. And I guess in the there is still work going on. This we haven't finished here. There's some tornado researchers who are interested in sort of how this fits in with other sort of tornado type events. Looking at various pieces of evidence, like if the weather stations didn't say much, we're looking at the models, looking at things like atmospheric stability. And there were not any, so far as we've seen, there were not any real smoking guns, right? There was a highly unstable atmosphere at the very beginning around the ignition, but then overall stability during most of the event, dropped down significantly. It wasn't a very unstable atmosphere when the fire breached, into the Jasper townsite. And yeah, I think that upper air piece of stability and atmospheric profiles of wind and temperature is going to be, you know, a much, you know, is identified now as a very important data source for, you know, future sort of predictions. It's very hard to bring into fire behavior models. You know, there are interesting sort of research models that use more atmospheric, you know, coupled fire atmosphere models, but they generally have trouble with rate of spread. You know, spread rate is the hardest thing to get on, and the most important. And generally, spread rate models are empirical, and so it's hard to get how, you know, you could get light winds of 6 kilometers an hour, you know, generating 90 meters a minute of fire spread from a plume-driven fire. I showed that one slide showing the you know, the Veers image with the smoke plume going, you know, sharply towards the east. Well, the fire was moving northward during that time. It wasn't moving to the east, but the plume was moving to the east. So that's a very nice illustration of how, you know, things are complex in the fire environment, especially when we bring in that third dimension. And I think we need to work together. I don't think the meteorologist or physicist or anyone alone is gonna solve it. It's an interdisciplinary science, and we're gonna need, you know, we're gonna need to bring in all our full bag of tricks to do a better job going forward. So
Yeah, and I think too, I feel like often in fire, there's just, like, the importance of terminology, right? And so people hear fire tornado, they analyze it, or they think of a, you know, a tornado from a supercell storm happening, when perhaps this note in the chat is more accurate, of it's more of a perhaps there's more of a vortex, more of analogous to a dust devil versus a tornado itself. And then just to clarify, those wind speeds you're talking about, for those who may not know, would be primarily caused then by the indraft from the plume-driven fire itself.
that's right. By the very strong energy of the, you know, the heated air of the column, you know, rising vertically, causing very strong indrafting. And then there was that one nice photo of the rotation, you know, so there's a rotational force generated there as well. And yeah, the evidence suggests that's really the fire and atmosphere generating that, but not really the wind. Possibly the slope as well. There was definitely some steep slopes there in, you know, the slopes of Mount Edith Cavell and other mountainous features. It is, you know, it's the Rockies. There's big mountains all over the place. But then also some of the most violent behavior was down at the valley bottom. You know, Wabasso campground, for those who know Jasper, was just decimated with some of the most intense kind of, you know, blasting, as I mentioned, of you know, stripping bark and wood from trees from the actual wind, you know, and you know, gravel basically blasting the fuels. So it's I don't think we solved a lot of the big questions, but we tried to document them, at least, of the phenomena. So
Yeah, and I think that's the intention, though, right? Is to document, and we're just building up our index of things to look into in the future, and with each event we add to that knowledge, right? Okay, so that puts us at time. I would like to thank Luke and Daniel for joining us today and being so open and sharing about these reports. And everyone who came to join us, thank you for taking time out of your Friday. I really appreciate it. It was really nice to be able to kind of hear what you thought were your key takeaway messages from each report. For those of you who haven't seen, the reports are posted a couple times in the chat. We will be sure to share them as well when we share the recording of this video sometime next week. So thank you, Luke, and thank you, Daniel. I hope you have a beautiful weekend, and we'll see you all at our next Canada Wildfire webinar.
thanks very much, Karen, and thanks everyone for great questions and participation.
Thanks. Bye, everyone. Take care.